Hello and welcome to the second video on Newton's second law of motion. And in this video, we are going to look at how we apply this law, especially in problem solving. And without wasting time, let's go to the very first question, which basically sets the stage for us to get into problem solving mode. And in this question, we are asked that in the topic of dynamics, the equation F is equals to ma is very important. Define all the terms in this equation. Define all the terms in this equation, which we have been told is very important. F is equal to ma. Let's start with the F. F is the resultant force which acts on an object. A resultant force which acts on an object of mass m, and when it does that, it produces an acceleration a, which is in the direction of the force. It is just as simple as that. F is the resultant force which acts on an object of mass m in kilograms. And when it does that, because it is a resultant force, it produces an acceleration a on this object, and this acceleration is in the direction of the force. The second question is closely related to that equation because we asked to define the Newton. And this one stems from the equation F is equal to ma. So the Newton is defined from this equation or stems from this equation. Remember, a unit of measurement of a certain physical quantity, they're usually stated after the equation which is associated with that definition has been written down. So here we were able to define force from Newton's second law of motion, and we say that force is the rate of change of momentum. This is the resultant force. This is the rate of change of momentum. And we say that the SI unit of force is Newton. So it is at this point that we can be able to define 1 Newton as the mass which gives as the force or resultant force, which gives a mass of 1 kilogram, an acceleration of 1 meter per second squared. Or when a force of 1 Newton acts on a mass of 1 kilogram, it gives it an acceleration of 1 meter per second squared. So in words, this is what you will write down. The Newton is the force that gives a mass of 1 kilogram, an acceleration of 1 meter per second squared. It is just as simple as that. These are the preliminaries as far as the Newton's second law of motion is concerned. You need to know the law, the mathematical statement of the law, and what each one of the symbols represent. Then from there, we need to define the Newton, because it is from this law that we define force. And once we have defined the Newton, we are now set to look at a question such as this one. We are given a car of mass 1000 kilograms traveling along a straight horizontal road, and it has an acceleration of 1.8 meters per second squared when a driving force of 2.6 kilonewtons acts on the car in the forward direction. So if this is the car and it has an acceleration of 1.8 meters per second squared, and you know that this car has a certain driving force, Fd, and there is a certain resistance to motion, Fr. You can say it is a resistance force, you can say it is a viscous drag, we can say it is friction force on the bodywork of the car, and so forth. Point is, the car is moving to the right like that. So Fd is one of the forces which is acting on the car. It is a driving force. It is a force which is developed by the engine of the car, while this is the resistance to the motion. So you can see there are two forces which are acting on this vehicle. So when we write this equation, F is equal to ma, remember what we have said in the first question when we were asked of the significance of F. F is the resultant force. It is not just any force which is acting on the object. It is a resultant force. So when we have two forces acting on this object, and we can see that the acceleration is to the right, then we conclude that the driving force is larger than the resistance. And therefore, for us to get the resultant force in the direction of the acceleration, we must subtract the smaller force from the bigger force. So we do the driving force minus the resistance to the motion, which is equals to ma. And by substituting here, we are told that this one is 2,600 newtons minus the resistance force is going to be equal to 1,000, because that is the mass of the car, times 1.8. And we can be able to see that after we have rearranged everything, Fr becomes equal to 800 newtons. And this is 0.8 kilonewtons. And the solution to this question is just as simple as that. You know, I may have written a lot here, and sometimes when we write a lot, it scares some students. You need not be scared, because you only need to understand what is happening at each and every stage. Another method that you could have used is to work out the resultant force. Which is ma. Ma is the resultant force. It is 800 newtons. And then you say the resultant force is to the right, 800 newtons. And we've got Fd acting to the right. If the resultant force is 800 newtons and this is 2,600, how much is this force here? So that question was just as simple as that. Let's look at the next question. Question 4, we are given that a metal sphere is falling at a steady speed in a tube containing oil. Describe all the forces acting on the sphere. So if this is the sphere, one of the forces which is acting on the sphere is its own weight vertically downwards. Weight acting vertically downwards. Another force is the up thrust acting on the sphere. The other one is the viscous drag. Which we can say D. Those are the forces which are acting on that sphere. This is the frictional force on the sphere by the liquid or by the fluid, because it is moving through a fluid. So that frictional force on the object, which is exerted on the object by the fluid in which it is moving, is referred to as a viscous drag. Or simply put, you can just call it frictional force. Then this is the up thrust on that object, and this is the weight of the object. We'll not go into the equations, how this one is calculated and all that, because we have just been asked to describe all the forces, and by description we name the force and state the direction in which it is acting, and we can even state what it is due to. Now, since this object is moving at a steady speed, it's falling at a steady speed, we realize that the acceleration will be 0. If the acceleration is 0, it further implies that the resultant force is 0. Just from this equation, F is equal to ma. That is why I said from the first question here, being able to understand what F is very important. It is not just any force which is acting on the object. It is that a resultant force which is acting on the object. It is the sum of the forces which is acting on the object. It is that single force which represents all the forces which are acting on the object. For example, here, there are three forces which are acting on the object. From this equation, since the speed is steady, that is, it is moving with constant velocity vertically downwards, then the acceleration is 0. If the acceleration is 0, you multiply 0 by whatever mass, this is the mass of this particular sphere, you're going to get a resultant force equal to 0. So this we are going is to say it is equal to 0. So the net force is 0. If they were to go ahead and ask us to state the relationship between all the forces, that it means sum of the downward forces, but remember this one has not been asked for. I'm just extending this argument for better understanding of this question. If they were to ask us to state the relationship between all these three forces, then we'll say sum of the downward forces is equal to sum of the upward forces. And that is how the three forces are related. Let's look at the next question. In question 5, we're given that we have a 110-gram apple. This apple falls off a tree. Calculate the weight of the apple. This one is very simple because we are going to say that the weight is going to be equal to mass times the gravitational field strength, and this is 0.12, that is kilograms. The value of the gravitational field strength, I'm going to take it to be roughly 10 Newton per kilogram, and that means this is 1.2 newtons. That is the weight of the apple. Of course, the other forces that we have discussed in the previous question also apply. Why do we say that they apply? You see, this object here is falling through this oil, is falling through the oil. That one is a fluid. This apple is also falling through air. So there exists upthrust and there is viscous drag. So how it is falling, we've not been told how it is falling. So we cannot go beyond that particular point. But as far as its weight is concerned, this is how we calculate its weight. Whether it is in motion, whether it is falling freely or stationary, close to the Earth's surface, its weight remains the same. Remember, that one is very important. Its weight is the same, whether it is falling freely or it is stationary, so long as it's close to the Earth's surface. Let's look at question number 6. In question number 6, we are given the diagram of a parachutist. The diagram shows a parachutist of mass 82 kilograms falling towards the Earth. Okay. In each case, determine the net force. Net force. Net is another word for resultant force. Net force is the same as the resultant force, and the acceleration of the parachutist. Here you can see that when we use the equation net force is equal to ma, we are going to see that the net force is going to be equal to 800 minus 300, which is 500. The mass of the parachutist is 82 times A, and we are able to calculate the acceleration of this parachutist vertically downwards. You can be able to calculate that because simply A is equal to 500 over 82 meters per second per second. In this other question here, the force acting on this person vertically downwards is 800 newtons, and the force resisting that motion is 800 newtons. If these are the only forces acting, then from F is equal to ma, we can see that the resultant force is 0. And therefore, even if this one is 82 times A, we are able to see that A is 0. How about in a question like this? The parachute now has opened. The viscous drag now becomes larger than the force acting on this object downwards. However, we are still going to maintain the acceleration vertically downwards. Let's see how we calculate that. From F is equal to ma, the force acting in the direction of the acceleration is assumed to be larger than any other force which is acting in the opposite direction. It's very important. If we have already indicated this to be the acceleration of the object vertically downwards, then we have to assume that 800 is larger than 1500. All right? And here we get m, and this is 82. This should be 82 times a. Okay? Then here we are going to get minus 700 is going to be equal to 82a, and the factor remains that a is negative. Okay? A has a minus sign, and that is expected because the resultant force obviously from this diagram is vertically upwards. So this is one of the situations whereby the resultant force and the acceleration, they are in opposite direction, and that fact is represented by the negative sign. Right? Let's move to the next question here. The gravitational field strength on the surface of Venus is 8.77 Newton per kilogram. Calculate the weight of a 5 kg rock on the surface of this planet. So weight is given by mass times gravitational field strength, and this will be a 5 times 8.77, and this one will be so many newtons. That one is not a problem. B, we are asked to calculate the weight of a similar rock on the Earth's surface. Again, when we use W is equals to mg, we're going to have 5 times the value of the gravitational field strength on Earth. It's 9.81 Newton per kilogram, but we're going to approximate that to be 10 Newton per kilogram, and that will give us 50 newtons. So you can see obviously that if you work this one out, you'll find that the weight on Venus is less than the weight on Earth. Reason being, why has the weight changed and the mass is the same? Weight changes from place to place because it depends on the value of the gravitational field strength. And you can see since G is less on Venus compared to on Earth, then the weight on Earth is more than the weight on Venus. This is one of the examples where we say that the weight of an object changes from place to place, and you can be able to see that when an object of the same mass is taken to a place where the value of the gravitational field strength is different, its weight will definitely change. Let's look at this question number 8. The diagram shows the horizontal forces acting on a motorbike and its rider traveling along a level road. The total mass of the rider and the motorbike is 160 kg. Determine the acceleration of the motorbike. So the acceleration obviously is in this direction, A. So by using F is equal to ma, the forces which are acting in the direction in which the motorbike is moving, which is this driving force, 380 newtons, minus actually it's 380 newtons plus 20. You can see there are two of them, this one and this one. They are acting in the direction in which the motorbike is moving. The force which is opposing that will be 70 newtons, and of course MA 160 A. So this like 400 minus 70 is going to be equal to 160 A, and you can see this one is 330. When you divide that one by 160, we get the value of the acceleration of the motorbike. That's how we get the acceleration of the motorbike. Again, use your calculator to get this value. It's just as simple as that. How about a car which is moving on a horizontal ground? The diagram shows the horizontal forces acting on a 920 kg car. The total forward force acting on the car is 400 newtons. Forward force, meaning the driving force, is 400. The drag on the car depends on the speed v and is given by the expression this much. So the higher the speed, the higher will be the viscous drag, this drag here. At a particular instant, the car is traveling with a speed of 20 meters per second. That means that that drag will be equal to 0.3 times the speed squared, that is 20 squared. That will be 400 times 0.3. This is like 400 times 0.3. 0.3 is like 3/10, and that will mean that the viscous drag is 120 newtons. Okay, 120 newtons. And how much is the forward force? 400 newtons. So therefore the resultant force is going to be equal to 400 newtons minus 120, and that means this is going to be equal to 280 newtons. That is the net force which is acting on the car. How about the acceleration of the car? The acceleration of the car is given by the resultant force, that is the net force, divided by the mass of the car. And we have seen that the net force is 280 newtons, divided by the mass of the car, which is 920 kilograms. And you can be able to work out that acceleration of the car. Okay, let's look at part B. Explain why you cannot use the equation v is equals to u plus at to determine the velocity of the car after time t. We cannot be able to use this equation because we have to remember that this equation, this kinematics equation, they are used where the acceleration of the car is uniform. That's why they are called equations of uniformly accelerated motion. So you cannot be able to use these because we can see that the acceleration of this car is changing. Why is the acceleration of the car changes? Imagine that the speed of the car increases beyond 20, becomes larger than 20, maybe becomes 21 meters per second. When that is the case, the viscous drag is going to increase. That means that the resultant force is going to reduce and the acceleration is going to reduce. It's very important for you to realize that this is one of the situations whereby the acceleration of the car is not uniform, and therefore equations of uniformly accelerated motion cannot be used in this situation. Okay, let's look at the last question, which is about a person in a lift. The diagram shows an 80 kg person in a lift. The normal contact force acting on the person from the base of the lift is R. So from the base of the lift, there is a force which is acting on that person, which is R, and there is the weight of this particular person. And then we asked, determine the magnitude of R when the lift is traveling upwards at a constant velocity. Constant velocity. Since the velocity is constant, then it means that the acceleration is 0. If the acceleration is 0, it means that F, resultant force, is also 0. When that is the case, it means that the sum of the upward forces, which is R, is equal to the sum of the downward forces, which is the weight. And the weight of this person is 80 times. Let's again take the value of the gravitational field strength to be 10, and we find that will be 800 newtons. So the value of R will be 800 newtons. It will be equal to the weight of the object. But in part B, where we are told that the acceleration is 2.3 meters per second squared, then we've got to use the same equation where we say F is equals to ma. F, we're going to say that since the acceleration is upwards, then R is larger than W. So we are going to say R minus W, which is 800, is going to be equal to 80 times 2.3, and you can see that the value of R now this time will be 800 plus again 80 times 2.3. You can work that one out and you will find that the value of R is larger than 800 newtons. At this point, maybe we can mention that the value of R gives us, if this person was standing on a weighing balance, the weighing balance will always read the value of R. If this person was standing on a weighing balance, which reads in newtons, it will be giving the weight, the apparent weight of that person in that lift, and that apparent weight is always given by R. So if you're asked to calculate the reading of the lift of this person when he is in the lift, they are asking you to calculate the value of R. And these are some of the examples that I've been able to pick in order to show how Newton's second law of motion is applied. And remember where we started from? We started by defining each and every term in this equation. And it's my hope that you've been able to see how I've used that equation throughout this discussion. See you in the next video.